I just request you to unmute yourself and let me know in case you don't see the slide or you don't hear me. Otherwise, since I'm on full screen, I cannot see the notification.
Yes, ma'am, I'm here.
Okay. So let's get started. My name is Debarati Chatterjee. I am a faculty at IUCAA. Welcome to today's lecture. So this is part 2 of the introductory lectures on compact stars as a part of the IUCAA Summer School and Refresher course this year. So if you have already attended my previous lecture, you would know that I talked a little bit about pulsar astronomy, how multi-wavelength and multi-messenger astronomy can help us to derive astrophysical observables that are relevant to neutron stars. And in this lecture, we will try to understand the internal composition of neutron stars and how we can relate them to these astrophysical observables. So what are compact stars made of? So we already saw yesterday that white dwarfs are mostly comprised of carbon and oxygen nuclei embedded in a sea of electrons. On the other hand, neutron stars have a much more complicated structure. But the reason why we call them neutron stars is that the core, which controls most of the mass of the neutron star, actually comprises of mainly neutrons and a small fraction of protons and electrons. And then there are more complicated compositions coming into play when we go to higher densities in the inner core. We will talk about this in a little while. But for practical purposes, we can assume that neutron stars are comprised of neutrons. So, like you already know, there are a lot of jokes about it. It's really a cliche, but yeah, physicists like to make simple hypotheses. So yeah, like the spherical cow, we are just going to assume that white dwarfs are comprised of electrons and neutron stars of neutrons. And let's see how we can deduce the mass and radius of such stars. So if we assume that neutron stars are made of electrons and neutrons, compact stars are made of electrons and neutrons, we know that these are both fermions. And like I mentioned yesterday, fermions obey Fermi-Dirac statistics. And thanks to the Pauli exclusion principle, fermions actually obey social distancing amongst each other. So basically the particles, they arrange themselves in higher and higher states with only one particle occupying a particular state. Bosons, on the other hand, they can be at the lowest energy state, and boson condensation also plays an important role in neutron star interior. We will come to that later. So according to Fermi-Dirac statistics, we know that at a particular density and at a particular temperature, so we are considering zero temperature for cold and dense neutron star matter. So all the energy states up to a particular energy level called the Fermi level are occupied. And in the inverse picture, in the momentum space, we can say that all the interior of the Fermi sphere is occupied. So all the energy levels up to the Fermi level are occupied. So from this Fermi-Dirac statistics, we can derive the number of states at a given momentum, say momentum k, per unit volume. So you can see the formula at the bottom, and if we integrate over these number of states, we obtain the number density, which is the number of particles per unit volume. And so this gives us a relation between the Fermi momentum and the density. Now, taking the number density, if we integrate it, if we integrate over the kinetic energy per particle up to the Fermi level, then what we obtain is the energy density, which is the energy per unit volume. Now, using the first law of thermodynamics, we can obtain the value of pressure, which is related to the density or to the energy density. And this relation between pressure and density, or pressure and energy density, is also called the equation of state. This is a very useful notion in astrophysics, because this actually helps us to derive a number of important quantities related to the thermodynamics of stars. So one can also obtain the energy per particle of such a system, and this is actually the energy density divided by the number density. So from the Fermi-Dirac statistics, we obtain a simple relation between the pressure and density. And if we assume a simple power law kind of relation between the two, as is shown in the slide, so P is equal to K rho to the gamma, or we can also write it in terms of the polytropic index. This is by definition, gamma is 1 plus 1 over n. So this simple power law relation between the pressure and the density is called a polytropic equation of state. This is the simplest kind of equation of state one can imagine for a compact star made of fermions. So if we consider white dwarfs, we are talking about electrons. And so there are two particular cases which are very interesting. One is if we consider non-relativistic electrons, which means that in the formula that you obtain on solving these equations, you put the Fermi electron Fermi momentum much less than the electron mass, then you obtain a relation where the gamma is 5 to the third. And on the other hand, there is the other extreme where the electrons are ultra-relativistic, which means that their momentum is much larger than their S mass. Then you obtain a relation where P is proportional to rho to the four-third. And then the two constants, K non-relativistic and K relativistic, depends on the electron mass. So taking such a polytropic equation of state, we now want to integrate in such a way that we obtain the structure of a white dwarf. So the structure means the mass and the radius. So for that, we assume hydrostatic equilibrium like we did before. So we assume that gravity balances the degeneracy pressure coming from these degenerate electrons. So in the figure, you can see that there is a shell of in the star of radius segment dr. So if you actually equate the change in pressure with this change of radial coordinate dr, then you can equate it to the change of gravitational force, and this gives you the Newtonian structure calculation equations. So if you now integrate from the stellar center outward to the stellar surface, so from r equal to 0 to r equal to capital R, which is the radius of the star, the condition is that the pressure and the energy density at the center are given by EC and PC. So these are the central values that we obtain from the equation of state. And at the surface is defined by the radius at which the pressure goes to 0. So if you integrate these structure equations, you obtain this mass radius relation, which is shown at the bottom. And basically, the maximum mass obtained is the Chandrasekhar limit that we talked about yesterday. So it's about 1.44 solar masses. And so these equations can be solved analytically. In that case, it's called the Lane-Emden equations. So when I give out the note, when I give out these slides, I will put the derivation of the Lane-Emden equation as well in the appendix. And these can also be solved numerically. So one thing important to remember here is that although the pressure in white dwarfs is dominated by electrons, it's the nuclei that dominate the density. So ultimately, we obtain the Chandrasekhar limit as the maximum mass. So if we do the same exercise for neutrons now, for neutrons, we need to remember that we cannot use Newtonian calculations because these are extremely relativistic systems. So there are some correction terms which appear, and these two equations with the correction terms are called the Tolman-Oppenheimer-Volkoff equations, or the TOV equations of hydrostatic equilibrium. In these equations, if you take the non-relativistic limit, which is when the pressure is much less than rho c square, and so Gm by Rc square is much less than 1, then these two equations reduce to the Newtonian equations that we saw in the previous slide. So now if we numerically solve these coupled equations in the same way, we see some interesting things. So first of all, we see that there is a maximum mass clearly appearing in the mass radius diagram. This is because the ratio of the pressure change with the change in energy density is actually the speed of sound. And in relativity, the speed of sound is less than the speed of light, because this is the maximum possible velocity according to relativity. So this actually limits the change of pressure to the change of energy density, and therefore gives a maximum mass possible. Beyond this maximum mass, the curved part of the mass radius diagram that you see is actually unstable. Another interesting feature, if you see, is that the mass obtained, the maximum mass, is actually pretty low. And this value of about 0.7 solar masses is also what was obtained by Oppenheimer-Volkoff when they actually derived this. However, we know from observations of neutron stars that the masses are around a canonical value of 1.4 solar masses. So what are we missing here? First of all, we know that in free space, neutrons are unstable. So they should decay into protons and electrons and neutrinos. So neutrinos would leave the system. In the case of finite nuclei, this beta decay equation that I just talked about is possible if the final states are not occupied. So if the proton electron states are not all occupied, so this would be possible. The generalization of, or the ideal case, the generalization of this of finite nuclei is infinite nuclear matter, where the system is still symmetric in neutron-proton, it is infinite, and it is bound by the strong force. In the case of neutron star matter, however, the matter is extremely asymmetric. We know that the number of neutrons in the system are much larger than the number of protons, electrons. So these neutrons, when they try to decay into protons and electrons, there are already protons and electrons occupying the low energy states, which means that this decay of that we see of neutrons in free space is not possible. So basically, the matter, the neutron star matter, is defined by two important conservation conditions. One is charge neutrality, and the other is chemical equilibrium. So the chemical equilibrium comes from the above equations, so beta minus and beta plus decay, that is neutron going to proton, electrons and neutrinos, and protons having electron capture, producing neutrons and neutrinos. And the equilibrium of these two equations give us this relation between the chemical potentials, where chemical potential mu is the derivative of the energy density with respect to the number density, and it is equivalent to the Fermi energy in the system. Charge neutrality, on the other hand, is very important in astrophysical systems, because the neutron star is not bound by strong force that you see in in finite nuclear matter or symmetric nuclear matter, but it is actually charge neutral. It has to be charge neutral. It is bound by gravitational force. So because if you have a charged object, if you have charged star, then the Coulomb forces would be strong enough to disrupt the star. So we need a charge neutral system. So now let's put, instead of just having free neutrons, we add the kinetic energy due to protons as well in the equation. And now if you repeat the same exercise, you see that the mass radius diagram looks like this, which is strange because the maximum mass is still very low. In fact, it is even lower than what you had when you had free fermions, free neutrons. So what are we missing here? So the missing thing is actually interaction between the nucleons. So nucleons undergo strong interaction amongst themselves. And so in addition to the free kinetic energy of the neutrons, we need to include the potential part, which is the interaction between the nucleons. And this is something which complicates the whole exercise, because now you need to understand the behavior of strong interaction at such extreme conditions. So there are different theoretical models for describing the nucleon-nucleon interaction, and there are large uncertainties and discrepancies between them. There are two main classes. One is called the ab initio models, microscopic origin. They start from realistic nucleon-nucleon interactions, and depending on what is the mechanism with which the interaction is generated, there are different types, like meson exchange models, such as Bruckner-Hartree-Fock models, where a mean field due to the background nucleons is assumed, and then the free nucleon is assumed to interact with this mean field. There are chiral perturbation theories and so on. And these give us important information about the behavior of nucleon-nucleon interactions at low densities. But the uncertainty in such models increases when you go to higher densities. So I will talk about this in a minute. The other class of models are called phenomenological models. Phenomenological means that they are actually, they involve density-dependent interactions, and they have some parameters or couplings. And these parameters are adjusted in such a way that they can reproduce the nuclear observables, the nuclear experimental quantities. And of course, there are also classes in such phenomenological models. There are non-relativistic models like SCRM or GONI models. And the problem with non-relativistic models is that although they are much simpler to handle, the problem is that they become causal at high densities, which means they do not obey the causality, the maximum speed of light limit. And the other problem is that without involving three-body forces, which means not only nucleon-nucleon, but nucleon-nucleon-nucleon interactions. So if these are not included, then the non-relativistic models cannot explain the saturation properties of nuclear matter. On the other hand, relativistic mean field models, so relativistic phenomenological models have had some success in reproducing these empirical quantities. In such models, the exchange between, the interaction between the nucleons is mediated by mesons. And these couplings of nucleons is fitted to bulk nuclear properties or properties of nuclei. So just to give you an example, so I'm not going into the details of the model, but just to give you an example, so this is a relativistic mean field model. On the right-hand side, you see a figure of the nucleon-nucleon interaction potential with distance between them. And you can see that there is a peculiar behavior, and this behavior is well known from nuclear experiments. So there is a repulsive core, and there is a long-range attractive force. That is very typical of the nuclear potential. And in the meson exchange model, it is imagined that the repulsive course is the repulsive interaction is of nucleon-nucleon interaction is mediated by the vector omega boson and vector omega meson, and the long-range attractive part by the scalar sigma meson. So apart from the sigma and omega, there is also a rho meson which takes into account the isovector properties, which means the difference between. Can you see me?
Yeah, we can
Yes,
see you.
ma'am.
Okay, because we had a power failure.
Power cut.
Okay.
Yeah.
So I was talking about the rho meson, which actually mediates the isovector properties, which means the difference between the neutron and proton number. So such a model is described using very general properties of relativistic relativistic quantum field theory, like starting from the Lagrangian that you can see in this figure. So this Lagrangian can be written in terms of the different contributions, the nucleons coming from electrons, the electromagnetic turn, the different mesons I talked about, which mediate the interaction, and there are even non-linear mixing couplings between the mesons. So from such a Lagrangian, one can derive the energy momentum tensor, and from the energy momentum tensor, one can derive the pressure and energy density. So we have the equation of state. So this is to give you an example. There are, of course, in the previous slide, I talked about the other kind of interactions. So there are many different kinds of equations of state. This family of equations of state, in contrast with the polytropes, are called realistic equations of state because they deal with realistic nucleon-nucleon interactions. And one interesting feature of such equations of state is that the pressure density relationship can vary, and the slope of this curve actually tells us a lot about the interaction. So a lower slope is called a soft equation of state, and higher slope is a stiff equation of state. And this is actually very well denoted by a quantity called incompressibility. So incompressibility, or the compression modulus, is basically the slope of this curve and is related to the derivative of the pressure with respect to density. And if you now apply the Tolman-Oppenheimer-Volkoff equations to such realistic equations of state, as we did before for the polytropes, you obtain the corresponding mass-radius relation. And what is very interesting is that now the stiff equations of state, usually the ones coming from the relativistic models we talked about, they correspond to higher mass, whereas the softer equations of state, like the non-relativistic ones, they correspond to a lower mass. So now we can relate the equations of state, we can relate the nucleon-nucleon interaction with the astrophysical observables. So this is something very interesting. So the equation of state of neutron star matter is actually very well represented in this diagram, where we can compare with the other experimental observables that we obtain from terrestrial experiments and other types of calculations. So the strong interaction between nucleons is called, the behavior is governed by the theory called QCD, or quantum chromodynamics. And this phase diagram of nuclear matter is also called the QCD phase diagram. And this is basically a plot of the density on the x-axis and the temperature on the y-axis. So neutron stars actually lie at the bottom, very close to the bottom axis, because you can see marked by compact stars or proto-neutron stars. And this is because they represent the region with very low temperature, so temperature around 0, and very high densities. On the other hand, we have nuclei at around 1 time saturation density. So these are the nuclear experiments. And on the other hand, we have all these heavy ion collision experiments like the LHC, like CERN, like the FAIR facility at GSI in Germany, the NICA, and so on. And so this is the intermediate region in this QCD phase diagram between at intermediate temperatures and intermediate densities. On the other hand, the very high temperature, low density region of this curve, of this graph gives you the kind of matter relevant to the early universe. And this is accessible to QCD calculations, which use a technique called lattice QCD, where the interactions are described in a lattice, and these require very high computational power and so on. And these give us hints about high temperature, low density form of matter. So what we can see from this figure is that exactly the reason why just doing nuclear or heavy ion experiments cannot give us all the information that neutron stars can give us or compact stars can give us. And the reason is this, because we are looking at different parts of the QCD phase diagram when we are talking about experiments, when we are talking about astrophysical observations and the early universe. So the relevant region of this diagram is that of low temperature, that of high density, so density is higher than up from 2 to 10 times that of saturation density. And the other very important thing is that it is asymmetric in neutron-proton ratio. So you can see that there is a third axis, and the compact stars is on this other plane, the third plane, which actually depends on n minus np, which means the difference between the neutron and proton densities. So the information we get from nuclear experiments gives us an idea about the masses of nuclei and the binding energies of nuclei. So the binding energy can be described by the Bethe-Weizsäcker formula. And this is, this comes from basic nuclear theory. And this binding energy, you can see, comprises of different terms. So there is a volume term, and this assumes the liquid drop model. So basically in the liquid drop model, the nuclei behave like a liquid drop, which means that there is a saturated force. The force of interaction is saturated, and there are some corrections. Saturated in the sense it only interacts with the nearest neighbors, and there are some correction terms which have to be introduced to this bulk term. And these corrections are these corresponding terms that you see in the formula, the Bethe-Weizsäcker formula. So the first term is the volume term with the coefficient AB. Then comes the surface term. So you have to include the effect of finite surface. So the AS term, which is proportional to the surface, so it goes as A to the 2/3. A is the atomic mass. Then comes the symmetry term, which depends on the difference between the neutron-proton ratio. Then comes the Coulomb term, which takes into account the charges and so on. Now, when we are talking about infinite nuclear matter, so the idealized system, A and Z are very large. So if you take the limit of large A and Z, this binding energy reduces to two important terms. So one is, of course, the bulk term, and the other is this asymmetry term. And this asymmetry term involves the asymmetry coefficient called delta. So we come to this in the next slide. So basically the energy per particle that we obtain from the liquid drop model, this can actually be expressed in terms of the density and the asymmetry. And the reason is that now we are extrapolating far away from the nuclear saturation point, nuclear saturation density. So we are going to higher densities and higher asymmetries in order to describe neutron stars. So here in this formula, you see the first line, so the energy per particle, consists of an expansion in X. So X is actually n minus n0 by 3 n0. So this is just a normalized difference from the saturation density. And the coefficients ESAT, KSAT, QSAT, ZSAT are increasing, correspond to the increasing powers of X. In the same way, the second line, this actually corresponds to the asymmetry terms. So now, and this asymmetry coefficient, so delta is the difference between Nn and Np divided by the total baryon number density. So basically, for symmetric nuclear matter, Nn and Np are equal. We have equal number of neutrons and protons, so delta becomes 0. So we have only the first line in the energy per particle, and this is called, that's why the isoscalar part, because it means that isoscalar, so it's scalar in isospin. On the other hand, for pure neutron matter, this is the other extreme, the proton number is 0, we have only neutrons, and in this case, delta becomes equal to 1. So you've seen the figure that the energy per particle, so the binding energy is actually ESAT. So this is the first term in the expansion at N0, and the higher and higher terms, KSAT, QSAT, ZSAT, can be determined from nuclear experiments, but the uncertainties increase with density. So the ESAT is quite well known. The energy per particle is around minus 16 MeV at the nuclear saturation density, which is around 0.15 to 0.16 Fermi to the minus 3. The second term in this expansion is the incompressibility that I talked about, and this incompressibility is also around 240 MeV. And there is another quantity called the effective nucleon mass. So basically the mass in medium mass of nucleons, but we will not talk in detail about the nucleon mass in this lecture. So now we talk about the second term in this expansion. So basically, you see that if we write down the two terms, the two lines of this expansion, we can write it as the E0 as the bulk term or the isoscalar term, and the second one is the isovector term, which involves isospin, the difference between neutron-proton number, and delta square. So if you plot the energy per particle with asymmetry, you get a parabolic structure because you have only second order terms in this expansion. And the E2, similarly, similar to the previous expansion, we see that there are terms corresponding to the different powers of X. And again, in the same way, the symmetry energy and then the higher orders of symmetry energy are less well known. So the uncertainty increases with density. And so we have only very limited experiments which give us some information about the possible range. And the symmetry energy is around 30 to 32 MeV. And the slope of symmetry energy, so the L-sim, is around 40 to 60 MeV. So what are the experiments which give us an idea about this symmetry energy? There are actually a number of experiments. So there is the calculation of the neutron skin thickness for lead, for calcium, and these experiments are called P-REX and C-REX experiments. Although there is a very large discrepancy yet, but in future there are plans to upgrade these facilities and get better idea of the neutron skin. So basically neutron skin is the difference between the RMS radii of neutrons and protons. There are also other experiments like which determine the electric dipole polarizability. There are the giant dipole resonances of lead, measured nucleon masses, isobaric analog states, and so on. And these kind of nuclear experiments are performed at a number of nuclear facilities around the world, at CERN, at GSI, at Ganil in France, at INFN in Italy, at JINR, and so on. So from these, we have some idea about the symmetry energy and the slope of the symmetry energy, and also that there is an indication of a correlation between the neutron skin and the slope of the symmetry energy. This figure you can see at the bottom right of the screen. So interestingly, if you see so this is like a summary figure on the top left corner. You see a summary figure of all these different experiments. So in the plot, you see the symmetry energy represented by J and the slope of symmetry energy represented by L. And what you see is that these, depending on the model, you have actually a large discrepancy in the predictions of these values. And the reason is that the different equations of state, for example, for the phenomenological models, these are all fitted around different nuclear observables, and therefore they can well explain those observables, but the prediction for other observables may not agree. So in the same way, you can see that in the bottom left figure, you see the correlation between the skin, the neutron skin, and the symmetry energy or the slope of symmetry energy. And these are seen to be seen in several nuclei. But again, if you see the correlations between the symmetry energy, the K-sim and Q-sim parameters, which are the higher order parameters of the symmetry energy, with the slope, you see that these points, which are coming from different models, the Skirm model, the Bruckner-Hartree-Fock, and the relativistic mean field, they do not show the same correlation. So there is, we don't know if these are physical or spurious. There's different underlying physics in these different models, and therefore this leaves open the question as to what would be the ideal equation of state for a neutron star. Heavy ion collisions that I talked about, these probe the hot and dense part of the QCD phase diagram. And interestingly, they also give us some information, some complementary information about nuclear matter. But the matter studied in such systems is actually hot and dense, and it's also symmetric in neutron-proton ratio. So one thing that we obtain from such experiments is the flow of matter in nuclear collisions, and this flow of matter is shown to depend on the equation of state. So from this, we also get some constraint on the pressure as a function of density. And this is at intermediate densities. However, the caveat is that these conclusions strongly depend on the transport model, which is used to describe such systems. For the case of pure neutron matter that you see on the top right figure, the symmetry energy constraints are not sufficient. So the symmetry energy as a function of density that you see at the bottom right figure come from different relativistic and non-relativistic models, the stiff and soft equations of state, and you can see that the predictions may agree up to saturation density, which is 1, but beyond this, there is a very large discrepancy between the models. There is also another set of experiments, such as those performed at GSI called Kaon spectrometer, or the 4P experiment. And in such experiments, kaon production, sub-threshold kaon production in nuclear collisions is used as a probe for the incompressibility of equation of state. And it is shown that this data can very well be explained if we consider soft equations of state at around 2 to 3 times saturation density. So other than this, there is another important aspect of heavy ion collisions, and these are great proofs of strong interaction physics. So basically, they tell us about modifications of hadron properties in the dense nuclear medium, about phase transitions from hadronic matter to quark-gluon plasma, and so on. So basically, they probe strangeness production. So before we go to strangeness, we have to look at what are the fundamental constituents of matter. So basically, so nuclei consists of protons and neutrons, and these are in turn created, and these are in turn comprised of fundamental particles called quarks. And so these quarks can be, there are 6 different types depending on the masses, and the proton and neutron involve only the up and down quarks, which are the lightest ones. On the other hand, at the high densities which appear in neutron star interiors, the strange quark, which is the next higher mass quark, can start to appear. And this can appear in various forms. So these can appear in say 3 main forms. I mean, there are many other suggestions, but let's consider deconfined quarks. So basically a soup of quarks. There could be pairs of quark antiquarks, and these are called mesons. So there could be condensates of mesons which can appear in the core. There could also be hyperons. So basically these are like neutrons and protons, but instead of up and down, there are also strange quarks involved. So let us quickly look at how such particles can appear in the interior. So the kind of interactions which govern the the creation of hyperons is given by these 2 equations involving baryons. And this is similar to the beta decay, but now it involves decay from the baryon B1 to B2 and the capture of a lepton by B2 to produce a B1. And the chemical equilibrium is actually determined by these kind of equations, and can be summarized in a formula which defines the baryon number conservation. So the mu I, which is for any particle I, if you consider the chemical potential mu, it is then given in terms of mu n, which is the neutron chemical potential, and mu L, which is the lepton or electron or muon chemical potential, and governed by the charges Bi, which are the baryon numbers, and Qi, which are the charges. So again, we already talked about this. Neutron star matter always depends on, is always governed by conservation conditions of charge neutrality and chemical equilibrium. And this is what governs the appearance of particles. So in the strangeness fraction plot in the bottom, you see that these different baryons are appearing. So the neutrons and the protons in the beginning, at low densities, when the density starts to increase, when the threshold condition is achieved, the lambda, the sigma, and the cascade, these baryons start to appear. So in the previous slide here, you can see that in the baryon octet, the next higher mass baryons are the lambdas, the sigmas, and the cascades. So these are the ones which appear in this plot at high densities. And in the equation of state plot, you can see the blue curve, which is that of nucleons only, whereas when you consider hyperons appearing, so with and without interaction. So with interaction, you see the dashed yellow line. So in this case, you see that once hyperons appear, the pressure is released the pressure is decreased due to additional degrees of freedom appearing, and therefore a reduction in the equation of state, in the reduction in the pressure, or a softening of the equation of state. However, the uncertainty in such models is the interaction potential of between the nucleons and the hyperons, or the hyperons amongst each other. Next we look at kaons. So we also said that kaons are mesons which can appear at the cost of electrons or at the cost of neutrons, and this can happen, this condensation of antikaons can happen if the condensation threshold condition shown at the left figure is obeyed. So it's basically when the in medium kaon energies are less than the electron chemical potential, so the kaons start to appear. Then they appear as the strangeness fraction plot on the top right corner. You see that neutron protons actually start to populate the kaons at higher densities, and then the electron and muon numbers start to go down. And again, depending on the kaon optical potential, you can have different types of different slopes of equation of state. You see that in any case, kaons appearing give rise to softening of the equation of state. And also this gives rise to a phase transition, and the condition that governs the phase transition is again the baryon number conservation and charge conservation between the two phases. So in the figure, the yellow part is the hadronic and the hashed part is the kaonic pure phases, and in between there is a mixed phase which should also obey the baryon number conservation and charge conservation. In the same way, quark matter, pure quarks, can also appear in the interior of neutron star. And in the same way, there is a condition for phase transition, which is governed by baryon number and charge conservations. So this kind of construction is called Gibbs condition, because Gibbs construction is where you have a mixed phase between the pure hadronic and the pure quark phases. And so when you have more than one, when you have two conserved charges, you apply this mixed phase condition or the Gibbs phase condition. So in this way, you can have strangeness in the production in the interior of neutron stars, and this can actually appear as stable components. So let us quickly look at a few signatures of such strange matter. So can we identify the appearance of such strangeness containing particles from astrophysical observables? So let us look at hyperons. So for example, we already said that if hyperons appear, the pressure will be reduced. So you can see in the right-hand plot on the top, the equation of state being softened, and therefore if you solve the TOV condition, you get the maximum mass. So this should also be lower. And on the left-hand side, I showed you this figure yesterday. So basically you have the mass distribution of neutron stars, and recently at the bottom of the plot, you see some large neutron star masses being observed, so around 2 solar mass. And these would, in that case, rule out the population of models in this mass radius plot, which actually cannot satisfy the condition that the maximum theoretical mass is higher than the maximum observed neutron star mass. So this means that hyperons, because hyperon containing neutron stars have lower masses, so in that case they should be ruled out. But it was shown actually, so I have worked on this project as well, so it was shown that hyperon repulsive interaction can actually answer this question. So this hyperon puzzle, that whether hyperons can exist in massive neutron stars, and the question whether the hyperon interaction is really such repulsive will be answered soon by other hypernuclear experiments. There can also be signatures of hyperons in cooling of neutron stars. So in addition to the IUCAA processes I talked about yesterday, there can also be hyperon IUCAA process, and this could also lead to additional cooling and therefore affect the cooling of the temperature as a function of age of neutron stars. There can be also signatures of hyperons in gravitational wave emission. I talked briefly about R modes yesterday. R modes will be, the instability window of R modes would be affected if hyperons are present. There are the spatial axial W modes, and these would also be affected by presence of hyperons. There are also other signatures of hyperons. For example, they would control the core collapse and black hole formation. Also the remnant which is formed at the end of a binary neutron star merger, the stability of this remnant would also depend on the equation of state. So if you have hyperons, they would have a different stability, they would have a different time of collapse as with respect to that containing nucleons only. So this is not all. There are many other signatures of exotic matter. And the good news is soon in future, there will be many other nuclear and hypernucleon experiments that are going to give us good answer to the questions related to hyperon-nucleon interaction, related to hyperon-hyperon interaction. These are being planned at BNL, at KEK, at JPARC, and GSI. There are also future heavy ion experiments coming up, particularly the CBM or compressed baryonic matter experiment. This is going to look at dense matter at intermediate densities and going to answer questions about the behavior of strong interaction at intermediate densities. And finally, we have to put together the astrophysical observations, the nuclear and heavy ion experiments, and the theoretical calculations in order to understand pulsars, in order to understand neutron stars, which are acting as observatories in space to allow us to study matter at high densities. So here are some references for further reading. This is mainly about nuclear matter, about nuclear equations of state. So feel free to read them. And if you have any further questions, don't hesitate to contact me on social media or on email. I will take questions now. I would request you, however, to keep the questions relevant to the slides that I have shown in this lecture, because this is meant for undergrad students and refresher course. If you have any expert questions, feel free to send me an email. Thank you very much for your attention. And so let's go to questions now.
So we do not have any question today in Zoom, so you can move on to YouTube questions.
Okay. In case anybody asks questions now, feel free to put your hand up so we can go to the questions. So let me see.
So we have two hand up.
Yeah, maybe we can take the question because of the power failure. I have to reboot my.
Okay, so I am unmuting Himadri Saha.
Hello, ma'am.
Hello.
Ma'am, my question is that what does the symmetric and antisymmetric nuclear matter mean? And is it related to the wave functions or something like that? I couldn't understand basically.
The symmetry and asymmetry, it's basically, so it's just, I mean, I am talking about symmetry of the neutron and proton number. So whenever I say symmetry, it's actually what I mean by, it's called isospin symmetry. So isospin is something which differentiate neutron and proton in a nucleon. So basically, if you see neutrons and protons, they have, both of them have up and down quarks, and they have if you study nuclear physics, you will see that there are some properties of nuclei which are symmetric in neutron proton, which means that they don't see whether you have a neutron in the system or a proton in the system. On the other hand, there are some cases where it differentiates between the two cases. So basically, you think that in isospin space, you think that isospin is a property in which neutron and proton are thought to both be the same thing, a nucleon, but with two different isospins. So it's just like up and down isospin, plus and minus, so to differentiate between the two nucleons. So when I say asymmetric or asymmetric, so I mean asymmetric in number of neutrons and protons. So when I say symmetric matter, symmetric nuclear matter, I mean so the same number of neutrons and protons in the system, whereas when I say highly asymmetric, which was in the case of neutron stars, you have a much larger number of neutrons than the number of protons. Is that clear to you now?
I think it is clear to him. So we may move on to the next person. So by Juni.
Okay, let's move on.
Hello, ma'am. Good afternoon. Am I audible?
Yes, you are.
Okay. Ma'am, in the radius versus mass graph for a neutron star that you just showed during the initial slides, in the graph there was the graph which indicates that there was a loss of mass, like the mass is not too high at that point. So in that graph, it was
let's see.
In the graph there was a small spiral.
Can you see my screen now, or you can't, right?
No, ma'am, I can't see your screen.
Okay, yeah, just one sec. Let me go back. Okay, can you see my screen now?
Yeah, ma'am. The screens are visible now.
Okay. So are you talking about this mass radius?
No, ma'am. No, ma'am. Before this.
Okay, so like this one.
No, not this one. Not this one. It was the mass from the very graph from where we are finding that the mass is not yet that very high, and there was a mass loss. Probably in the slide 10.
Slide 10. Okay.
Yeah, that one.
Yeah.
That one.
Okay.
So there was a small spiral in the initials of the graph.
Yeah.
So could you please tell me what does the spiral mean actually, or what does it signifies?
This is actually related to the, in the previous slide, I talked about this. So basically this comes from the change of pressure with respect to the energy density. And this kind of snout structure, this kind of maximum mass, you will not find when you go to only Newtonian QB. Like for example, for this plot, you can see this was considering, this is white dwarfs, but the mass is at the bottom, 1.4. So you can see here, there is no such curve, right? So this is the Newtonian case. But even for white dwarfs, if you include the general relativistic corrections, then you will get this kind of a behavior. And it's coming from the fact that the pressure change with respect to energy density change in the equation of state, this is actually the speed of sound, and it is limited to the speed of light in case of relativistic theory. So actually what I should have put another plot here. So if you put the white dwarf masses and the neutron star masses in the same figure, you can see there is one branch for the white dwarf where it goes up, and then again there is an unstable branch. Then there is again the mass radius of this that you see in this figure of the neutron star, and this again comes down. So basically this snout is actually unphysical, it's unstable, it's an instability. So this branch, the left part of the curve beyond the peak, is an unstable branch.
Okay. Is that what observed, or it is just like theoretical calculation?
No. It's only theoretical calculation. That's what I said. What is observed is up to the peak. Up to the peak, this is up to the maximum mass. And beyond this, the branch is actually unstable branch. It only comes from theoretical calculations.
Okay.
And it can be shown from stability studies, it can be shown that this is actually unstable with respect to radial oscillations.
Okay, so is it like that in that unstable part? Hello?
Yeah.
Oh, so is it like that in the unstable part, those compact objects like behave somewhat like the Cepheid variables? Like they just mass just like...
No, it just collapses with respect to radial oscillations. So it's unstable to radial oscillations. It collapses with respect to radial oscillations.
Okay, thank you, ma'am.
Okay, there is one question on YouTube from Anudeep. Could you explain the multiple values of mass? Oops, the question disappeared. Is there any other question from YouTube? Okay, I don't know, the question disappeared.
There is one question from Zoom. Should I unmute?
Yeah, okay, sure.
I can't see her. Okay. Sweta, you are unmuted. Please ask the question.
Hello, ma'am.
Yeah, hi.
Ma'am, my question is, what does Q and Z mean in energy per particle equation?
Okay. So these actually L and J, right? I mean the J in that the other figure that I showed here. You mean this J and L? So the J here is actually, it's just a different notation. So this is the same as symmetry energy. So here in this expansion, that this is a Taylor expansion of the energy per particle. with respect to x and delta. So the first terms are for zero asymmetry, and the second line corresponds to asymmetry. And so the first terms, ESAT is actually the saturation energy per particle. So the energy per particle at saturation. KSAT is derivative of that with respect to density. It's also called incompressibility. The QSAT is the third derivative of energy per particle with respect to density. ZSAT is the fourth derivative, and so on. On the other hand, asymmetry is actually the derivative with respect to asymmetry. So basically del to E del delta square. And LSIM is the slope of that with respect to density. So del E sim del of X. And then, so all these terms, LSIM, KSIM, QSIM, ZSIM are the higher order terms of the derivatives of eSIM. Is that clear to you?
Yes, ma'am. Thank you.
Yeah, you're welcome. So I don't see any more update on the YouTube questions. So if there are no other questions on Zoom, then maybe I will wrap it up.
I don't see any other question in Zoom also, so I think we can wrap it up.
Okay, thank you so much, Bhaskar. Thank you everyone for your participation. And of course, if you have any further questions, don't hesitate to contact me. Thanks to the organizers of the IUCAA Summer School for giving me a chance.